I currently work for Med Institute in West Lafayette, Indiana, but we're just part of a larger a Cook Medical organization, which has entities throughout the world, and we're primarily a privately held medical device company, and we're going to talk specifically about a small subset of devices. Cook's history, its start in the 60s was transcatheter delivery of devices such as stents. Okay, Cook actually developed and had approved the very first coronary stent, for example. Long since off the market and been replaced by many other products, but to give you kind of a feel. And we're going to talk about, I'm going to use the stent as the example of choice here. The topic is really focused on the safety of these stents or any other kind of long metallic conductive device which we may leave in the body in a permanent fashion. And the question is, when we leave these stents, and I'm not in the silver stent that I have here is it's a vascular stent. It's self-expanding. It's made of nickel titanium, and it's used in the peripheral arterial tree. So iliacs and superficial femoral arteries. And so these things are relatively long. They can be 80, 120, 160 millimeters long. And the doctors have the options of basically putting them end to end or overlapping them slightly to make them basically almost any length. And as we're all familiar with, MR scanners as a great diagnostic tool, non-ionizing radiation, so everybody loves the safety. And the MR is essentially, there's three components I'd like to just touch on. It has a giant superconducting magnet, okay, which creates the static magnetic field. Typically 1.5 Tesla is a diagnostic machine. It's the power of the magnet. 3 Tesla is less common. But you'll still see that at most major medical centers. So you have this giant superconducting coil, which they pass a current through to create the static magnetic field. There's a gradient coil for creating a much smaller magnetic field, which varies in space. And then there's the part that we're really interested in. There's an RF coil that has to put RF energy in at a certain frequency to make this whole thing work. Okay, and I'm not going to be talking about the diagnostic, the science of creating the images. It's a whole field in itself, and there's a whole slew of experts that can talk to it. I'm really talking about the issue of when we put devices in people and we put it inside this RF field, that they can heat up. And typically, a long metallic device in a RF field will heat up at the ends. And this is kind of how I got involved in this. There's a little history. Coming to the COMSOL conferences since 2006, just kind of keeping an eye on the technology. We did not have it in-house. We had other tools, primarily the Abacus product that was used for most mechanical and thermal problems. But it's kind of my job to stay on top of the more advanced technologies. And this problem came along in 2009, and you can see basically this is a phantom. It's a rectangular acrylic device that's supposed to be like a little head up here. And it's filled with a gel which has the electrical and thermal properties that are average tissue properties, dielectric properties, average tissue properties. And we put our device in this phantom, put the phantom on the table, we slided it into the MRI, we turn on the RF coil for a typical scan time, and we put thermocouples at the ends of the stents, because that's where we expect things to be the hottest. We'll cover more of that later. And what we see on the top graph is 2 overlapped 80 millimeter silvers, which give you 160 millimeter length. And on the bottom, you have 80 millimeters. And you can see on the top, we got near some kind of resonant length, and it heated up to from 22 degrees, a room temperature test, to about 32 degrees, or a temperature increase of 10 degrees. And again, we're interested in safety. And the biomedical engineers can talk to this better, but if you expose tissue to temperatures, we generally like to see things under 6 degrees, but if you get over 6 degrees, depending on the kind of tissue you are and the length of time, you can do damage. Okay? You can do potentially permanent damage. So it behooves us as a device manufacturer to understand that this is the case and then try to design devices that don't show this kind of heating. So it was actually my roommate, who's the director of the bench testing lab, who came to me and said, hey, what are we going to do here? This temperature is too high. There's regulatory concerns as well. You know, everything has to have regulatory approval. But as a general philosophy of the company is we need to make these devices safe. What do we do? So we decided that as mechanical engineers, well, there's arterial flow, and the Phantom does not have arterial flow. So let's see with the tools we have, what will arterial flow do to this problem? So I kind of reverse engineered the problem, created a finite element model of the Phantom, and tried to recreate the test result. And with the tools that I had, there's no computational fluid dynamics at that time. I used Joule heating to heat this stent up. Yes, the mechanism of Joule heating is not what's really happening, but I create enough energy to heat the ends of the device up to match the test result. Then I make a separate model of a vessel, assume a laminar pipe flow that's fully developed. We iterate on a Nusselt number that seems appropriate. Assume that flow goes through even with a healing endothelial layer, which will cover the stent as it heals in the vessel. And sure enough, with a approximation of blood flow going through, the temperature rise goes from 10 degrees to 3.1 degrees. Okay? Now we're convinced that, hey, the blood will cool this. It will not really see 10 degrees. That was an artifact of the test. And actually, this went through regulatory approval, and everybody's happy. But the handwriting was on the wall that this idea of using really the wrong physics to create an engineering solution to a problem, you know, the time was limited before that was going to be called into question. So we need to create a RF heating simulation capability. And, you know, why do we want to do that? Primarily, again, safety. We want to prevent excess cell death by keeping the temperature down in this case. Our first thought was to use this tool primarily to complement the testing. So go into our devices, which have multiple sizes, lengths, as well as diameters and shapes, and say, hey, instead of having to test potentially dozens, maybe we can use this to just find resonant lengths and show that these are worst cases and test just the worst cases because there's not, and that changes as a function of the scanner that we're in, whether we're in a 1.5 Tesla or 3 Tesla. You have different RF frequencies, you have different characteristic wavelengths to deal with. So our idea was, let's just use the tool not to make an absolute temperature prediction, but to help us design a test matrix where we can then be satisfied of the safety of the device. Later on, we started running into a device, which I'll show an example, where it wasn't really a one-dimensional device, and then the question comes, well, we only have 4 thermocouples. Where do we place these thermocouples? Well, we place them where we expect it to be hottest. Well, if you've got a wire or a stent, it's kind of one-dimensional, you put it at the ends. But if it's kind of a 3-dimensional antenna-looking thing, where do you put the probes? Okay? And you have to justify where you put the probes to yourself as well as to, again, regulatory authorities. So simulation, we were hoping, was going to give us insight into this. We hope that it would, and I put this in italics, provide understanding. As you know, in an experiment, such as what I showed you earlier, there's these 4 thermocouples. They're special fluoro-optic couples that do not disturb the electric field, are not conductive. But you basically get really 3 temperatures of interest, because 1 is the background. So you get 3 temperatures as a function of time, and it doesn't really tell you anything else than that. And we're looking for simulation that lets you look into the problem and try to understand it better with the hope of being able to design better tests and better devices. And then finally, it's kind of presumptuous of us at this time to say this, but we're looking at virtual bench testing. In essence, is it possible to do simulation in lieu of testing? Okay, that would really rankle the feathers of a lot of engineers and regulatory folks, I think. But you can obviously see the advantage to doing so, and we'll talk a little bit more about that later. Is that possible? Okay, this is my only physics slide, and again, you can't ask questions on this slide. Okay. The basic nature of the MRI scanning is we have this big B0 static magnetic field, which I'm told will take your hydrogen nuclei and align the spin. So they're precessing kind of randomly, and then so it aligns everything. It aligns certain hydrogen nuclei, which are part of the water that's in your soft tissues. Okay, so they're aligned in this static field. And then we throw an RF pulse, RF energy at this aligned field, and if this RF energy is at the right frequency, the Lamar frequency, these hydrogen nuclei will tip. They will tip. They will flip 90 degrees, and then they will relax back some characteristic time. And from the nature of how they flip back and the density that they flip back and lots of details, they can use the receiving coils and software and diagnostics to make an image from that. And I'm not going to go into nuclear magnetic resonance imaging because I'm not qualified to. But all we really need to know is we need to put an RF energy into this to make the process work. And unfortunately, a side effect of putting this RF energy in is the devices heat up. Okay. So as far as physics is concerned, and I will not even begin to pretend that I understand Maxwell's equations, but certainly the term of a time-varying magnetic field is going to produce an electric field. And if we put a conductive element inside of this time-varying magnetic field, and you guys can certainly instruct me better than I know myself, you're going to disturb or scatter the electric field off the tip of a conductor, and you're going to have basically hot spots of electric field at the end. And that's a phenomenon that we want to capture. As far as calculating what the temperature is, we want to bring heat transfer in. We certainly have the diffusivity, the inertial time-varying term of heat transfer. You have your diffusion. We're really not going to talk much about perfusion. That is an approximation for a smeared capillary bed. Not important right now. The metabolism adds very little energy in the time that a 15-minute scan occurs, but we're coupling it into the electromagnetics by the RF energy coming into the heat transfer. That's what's really powering the thermal problem. And that's calculated from the first physics that we do, which is solve the RF problem. Okay. So after going to the conference for 3 years, sitting through most of the talks, which I have a fractional understanding of, and looking at the modules, it seemed to me that the physics available in the RF module and the physics available in the heat transfer module, CAD import module to bring in our devices. Even in the COMSOL Multiphysics, we have laminar flow to look at arterial flow in a simplistic fashion. It seemed like those pieces were there, okay? But the reality is, I don't have the time to go through the trillion iterations of the Library of Babel. In a corporate environment, you've got 9 or 12 months to show that you're going to make progress and get somewhere, or your funding gets cut off. And there is no library of any kind that exists, okay? The real world that we live in. I mean, I'd love to have a million monkeys on a million laptops. I'm sure they'd eventually get to the right set of commands to solve this problem. I don't know when they'd recognize that it is the solution, but it's not practical, okay? So how do I get where I want to get and get there relatively quickly? And I learned this. I was been part of this on one side, and I've been on the other side as well, and that's to just leverage off of people that do know. So there's lots of smart people around, and a lot smarter than I am. And the idea is to swallow your ego and get these people involved. So I met, after 3 conferences here, I met Jeff Crompton in the room next door and talked to him about this problem. And he said, you know, let's give it a go. We'll do a small phase 1 investigative work. And COMSOL's was successful with that, and their role is key into really kind of identifying the physics, identify, the devil's in the details. What exactly in COMSOL do we use to build this RF coil? How do we validate that we're getting the right solution? And actually practically get somewhere in a period of time and for a cost that is going to work out for you on a commercial sense. So really without Altasim's help, I wouldn't be standing here. And this one phase, this investigative phase that we went into to see if this would work was what we call phase 1. We must be, I'm throwing new phases at them all the time. We must be at 15 plus phases by now. As we keep having success, it's very easy to get, it's easier to get the funding you need to do the next thing that you want to do, okay, real world. So really, Jeff Crompton connected us with Professor Lon Simonetti at Ohio State, who is he's truly an MR expert in designing pulses for diagnostics. He has access to 2 research machines, 1.5 and 3 Tesla at Ohio State. So his knowledge of how, and he's a former Siemens employee. You can see where this is leading. So he has industrial knowledge, he has academic knowledge, he has the hardware and equipment and postdocs. And so he came onto the team, extremely important. And his previous contacts and employment with Siemens, when we ended up being able to talk to the engineers at Siemens to give us some details about the coils and the scanners and how they work and if what we're doing is reasonable. Okay, so very quickly here, we have how do we generate this RF field? Well, we create a birdcage coil, which is fed in a quadrature fashion. Voltage is applied to these ports, 90 degrees out of phase. They're 90 degrees displaced in space. And the idea is to create this uniform magnetic field in the center of the scanner. Okay, this is what the people need in order to produce good scans, a very uniform magnetic field at the isocenter or near isocenter of the scanner. And sure enough, the magnetic field that we calculate by building this in COMSOL gives us a 2 to 3 parts per million variation of the uniformity, which is acceptable and is practically acceptable and measurable. Next thing we do, and this is all part of the validation, is to bring a phantom in, which is just what I showed earlier. This is a Japanese standard. It's a round gel phantom. It has human tissue properties as far as its dielectric and as far as its electrical conductivity and its thermal conductivity. We put a round phantom in, and there's some literature with this round phantom where people have made measurements. So if we put a wire into this RF coil and we drive it at the right frequency, for 1.5 Tesla, it's approximately 64 megahertz. Sure enough, it resonates. You get electric fields scattering off of the tips of the wire, and you get you couple the physics, and you get high temperatures off at the end of the wire. Okay. And we go into literature, which is why we did pick this problem, and we can compare the results from COMSOL to that which we see that's done experimentally and with the method of moments, which is a numerical technique, but a much narrower numerical technique. We were very happy here in that we were really coming out to just try to predict what is the resonant length. Can we pick up the resonant length, which is, at what length does the temperature hit a maximum? Here it's 20 centimeters in this particular problem, and we did. Still not having a feel for how good are we going to be from an absolute temperature standpoint. Looks reasonable. But we're very happy that we can pick up the resonant length. So next we switch to going to Ohio State, and we switch the phantom to the ASTM phantom, which is a very similar gel-like material, but it's rectangular. And here you have a picture of what the electric field looks like when we power our coil on, what the electric field looks like, electric field norm on a 3 Tesla machine, if we just take some slices through it. And you'd kind of expect the electric field to be 0 near the center, its highest near the edges, and we test near the edge of the phantom, in the center of the phantom, in the middle of the gel, and off very close to the edge of the acrylic. So we take something called it's a titanium rod, 1/8 of an inch in diameter, 10 centimeters long, calibration rod. Ironically, it's called a calibration rod, and we put this into our ASTM Phantom and actually drilled holes in the tip, put in our thermocouples, and we power a test where the coil on time is 450 seconds, and then we turn the coil off and the thing cools down. And what we're doing here is part calibration. I basically don't know what voltage to apply to my coil. It's not something the manufacturer will give you. We don't know all the electronics and the RF amplifiers and everything. So we have this idealized coil. We have to apply voltage to a port. So we tune the voltage until I hit this maximum temperature. So we can't say that the simulation is predicting the maximum temperature accurately, but what it is showing is that it's solving the heat transfer problem quite well, because the shape of this curve is reflective of solving the transient heat transfer problem properly. Okay. So very happy with that. Kind of one of the money slides is we then go back to the silver stent, which I showed you, which is this intricately designed, laser cut, nickel titanium, 10 millimeter diameter, 80 millimeters long, and we put it into the 3 Tesla scanner, and we put the thermocouples at the end. Now we use the voltage that we derive from the calibration rod. We don't change it. We power it on. This is a 900 second or 15-minute test, and bang, we hit the maximum temperature within a couple tenths of a degree. Okay, so close that there were those who questioned that this was a real result. Okay. I was lectured a little bit by a few people that you don't normally see results align quite like that. I said, I appreciate that. And even what it appears, maybe we got the shape right, but we miss a little bit here. That has more to do with the term in the solver where you choose free time stepping versus strict. I didn't know about strict. Sergey had to instruct me that if you wanted to hit exactly your time off, coil time, off time, you got to use the strict solver, and that will really nail this this point here. So now we're getting very excited. Not only are we getting signs that we're getting to get the resonant length right, but now we're getting absolute temperatures to be, looks like that we'll have predictive capabilities to be very accurate. Of course, every time you do something like this, you're now raising the bar. You know, your management's looking at it, regulatory people are looking at it, you're looking at it. Now the bar's up here. When we set it first, it's going to be down here. Just give us resonant length. But that's okay. It's a good problem to have. Next set of devices that came along, I hinted at this earlier, are these vena cava filters, not very one-dimensional. They would be in the superior vena cava. They're supposed to catch blood clots after you've had some kind of surgical procedure. Catch blood clots before it gets into your heart. Good thing. And most of these are, and most of them are removed. After some period of time, they can go in and grab that hook and actually pull it into a catheter and pull it out of your body. Or they may leave it in. But in any case, they're in long enough where it's a possibility that you'll be scanned and they may heat up, and it's the same question. Can you keep the temperature under 6 degrees and feel good about the safety of the device? So we take this CAD geometry from ProEngineer in this case, which was 7-year-old CAD data, and I'm not going to go into the issues I had of trying to get that to a modern format. Okay, but very intricate. These wires are less than a millimeter in diameter. I pulled in the full resolution of the data, pulled it into COMSOL, struggled for many weeks trying to resolve domains and so forth with such crummy geometry information, slightly corrupted slivers and so forth, and getting it to resolve the tolerances. But nevertheless, into COMSOL, into the gel, it finally meshed. Workstation has 64 gigabytes of memory. It's, you write a check, it's a few $1,000s, you have it. 8 cores, runs for 2 to 8 hours, and you have a solution. And the solution one of the solutions looks something like this for the 2 types of filter. Tulip filter is the older filter, Select filter is the new generation filter. And what did we want to know? We really wanted to know, where do we put our thermocouples? Because the comment was made this is a complex structure. Where are the ends? Okay, and how do you orient the filter in the phantom? Well, we found an orientation that we thought was close to worst case. It looks like the hook is going to be hottest, not surprising, and that the major struts would warm up somewhat here, and the minor struts are these thin little wires here, that they would heat up a little bit. That was the expectation. But the analysis was really done just to show that we know where to put the thermocouples, and then that we'll feel comfortable with those results. But when we were done and we compared the data, not only did it predict relatively where the device was the hottest, which is the hook, which is we expected, it showed that we were under 28 degrees or under 6 degrees. When we started looking at the absolute comparison, that looked pretty scary again, where a very complicated structure like that with 18 million degrees of freedom running for 12 hours in this what I view as a complicated problem. And another money slide. Again, I didn't show this to the same people that critiqued the other. Well, actually, it's in a poster that's over here. They have seen it. It is what it is, and I'm not going to make excuses for the fact that it agrees very well, but it does. Okay, so the conclusions we draw are pretty simple. COMSOL Multiphysics can accurately, I underline accurately, can accurately predict what the device, or it's really the tissue. The heating occurs, the electric field scatters off into the tissue. It's the tissue that heats up. Your device is kind of like a heat sink. It's sitting right next to the hot tissue, and it draws the heat into it. But we can accurately simulate that temperature, validate it with various experiments now, and then be able to, it's the same slide I had before. We can determine safety. We can use it to supplement or complement the testing. We can find the locations of maximum heating. It gives us an understanding of how a certain device may perform in the phantom, and eventually, where I'm going with this is potentially in vivo. So it can provide us all the things we were looking for. And I've changed the question mark here to an exclamation mark. Can we do simulation in lieu of testing? Because sometimes the testing is problematic. Just getting the thermocouples, even in a vat of saline, getting the thermocouples where you want and having them stay where they have to stay and being very precisely in the location that you're looking for can be problematic. And then if you're going to extend this to some in vivo conclusion, then they don't let you test in humans, and animal tests are very expensive, and they're problematic because we're only talking about a few degrees of heating, and even an anesthetized pig getting in there and trying to measure these things, very expensive. So the real possibility, and where the industry is moving, is towards doing simulation in lieu of testing in some instances. Though we're still very complementary. You can see where we're going to get pushed to go towards actual, in vivo simulations. So, where we're going to continue to develop things, you never stop validating. You can never get enough data, validation data, so that you make people feel comfortable with the approach that you're taking. There's continually new scanners that are coming out. The coils are 60 centimeters in diameter. The newer ones are 70 centimeters. Primarily, people get claustrophobic. That's what the official line is. But the reality is, the Americans have more of these scanners than anybody else, and we're overweight, okay? And we're big people. So they need bigger scanners, and means bigger magnets, and it's more expensive, and so forth. And so we have to consider these newer coils. Higher field machines may be coming. The higher the field, the better the signal-to-noise ratio, the better imaging that you can get. But the higher fields tend to localize things more. The frequency is smaller. The characteristic wavelength is smaller. So you're going to have more heating issues. And we're going to have to look at that. Multi-channel RF coils instead of a quadrature-fed birdcage coil. We're going to individually control each of these loops. In a multi-channel, it's a way of tweaking these higher field coils to give a more uniform B1 field, magnetic field at the isocenter. There's no commercial manufactured MRIs that have that kind of coil yet, but you have to be prepared. You can't wait for it to show up and then say, hey, we have to figure out how to do it. There's always ways of looking at simplifying or idealizing your stent geometry to make the problem simpler and run faster and still give you an excellent result. That never stops in this field. And again, you can't wait for the iteration, the random iterations. You kind of have to intelligently focus. Including perfusion is very simple in COMSOL. Put a number, put it in, and go. But the idealization of how that really works and how the capillary bed really cools things, and is the core temperature of the whole body going to actually stay at 37 degrees, or is your whole temperature is going up? That has to be addressed. Vascular arterial flow, so we're going to couple this with CFD. We've already started that, and that works very well. So looking at arterial flow going through the phantom, essentially, and putting a device in this artery and seeing how much cooling you get to a moving blood flow. It kind of goes all the way back to the original analysis that I did with Abacus, where we just made basically a simple Nusselt number, or H, for Newtonian heat transfer out of a boundary, and used a couple CFD to see how good was the selection of that H. Looking at simulations where we're just looking at the effect of magnetic field on devices. Most of the devices I put up here are cobalt chrome for the filters and nickel titanium for the stents. Their magnetic permeability are very small. You put them near the magnet, not much happens. Not like my third watch I've been through, okay? But there are stainless devices that we manufacture, especially stent graft devices, and you want to know what the forces are in these devices, because even though the magnetic field is uniform in the center, so there's really no magnetic force on the devices, you have to pass through very near the point of the highest gradient of the magnetic field, so there are forces, and you want to ensure that your device doesn't migrate. Okay, doesn't migrate and stays where and functions the way it should. And then eventually, where you see the industry going as you go to the conferences and talks, is to take these virtual humans, which have been scanned by the IDIS Foundation and supported by the FDA, and instead of using a square phantom, we want to take a human being and put it into the coil. And there have been people and papers and publications to do this, but it's very difficult, and the interpretation of it is even more difficult. What makes our life more difficult is this is in a voxelized format, because they're using a finite difference time domain scheme to do this kind of problem, which has been the method of choice since the late 90s and early 2000s, because there were no 64-bit machines with memory. I just serendipitously come along in 2009 when 64 gigabytes is a write of a check with very little authority, and I can now use the finite element method and solve this much more sparse problem in its full beauty and complexity. So getting this digitized humans into a format in that we can actually use in a CAD format and import the parts of the anatomy that really matter to us is going to be a phase that we're going to be looking at, and it's going to be a challenge. But there are various tools out there to help one do this, as well as potential government industry partnered ventures to try to convert these models to what would be more classically thought as a CAD format rather than a voxelized format.